Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic electrical and electronics engineering. We'll dive into key concepts like Introduction to CC, CB and CE, transistor configurations. Slide 1. Introduction to transistor configurations. Let's begin with transistor configurations. In electronics, a transistor configuration defines which terminal of the transistor is common to both the input and output circuits. There are three basic configurations based on this idea. Common base, CB. Common collector, CC. Common emitter, CE. Each of these has a different arrangement of input and output terminals. Because of this, their behavior in terms of current gain, voltage gain, input impedance, and output impedance also changes. In CB configuration, the base is common. In CC configuration, the collector is common. This setup is also called an emitter follower because the output voltage follows the input. In CE configuration, the emitter is common and is the most commonly used setup in practical circuits. Example, if you open an audio amplifier circuit, chances are high that it uses CE configuration. The significance of studying these configurations lies in choosing the right setup based on what we need: voltage gain, current gain, impedance matching, or signal phase. A new term here is impedance, which in AC circuits includes both resistance and reactance, and it defines the opposition to current flow. Slide 2. Common base, CB, configuration. Now let's discuss the common base, CB, configuration. Here, the base terminal is common between the input and output. The input signal is applied between emitter and base, and the output is taken from the collector and base. One important characteristic of the CB configuration is that its current gain, denoted as alpha, is less than 1. This means that the output current is less than the input current. However, it has high voltage gain, so while it doesn't amplify current, it can increase voltage significantly. It also has low input impedance and high output impedance, which makes it ideal for high-frequency applications, such as radio frequency amplifiers. It's also important to note that the output signal is in phase with the input, no inversion takes place. Example, CB configurations are often used in TV tuner circuits. A new term here is current gain, alpha. It is the ratio of collector current to emitter current in CB configuration. Slide 3. Common collector, CC, configuration. Let's move to common collector, CC, configuration. Here, the collector is the common terminal for both input and output. The input is applied between base and collector, and the output is taken between emitter and collector. This configuration is also known as an emitter follower, because the output voltage at the emitter follows the input voltage at the base. The CC configuration has very high current gain, roughly equal to beta plus 1, which means it's good at increasing current. Voltage gain is nearly 1, so it doesn't amplify voltage much. The key advantage of CC is in impedance matching. It has high input impedance and low output impedance, making it ideal for connecting two stages of an amplifier circuit. Another benefit is that there is no phase shift between input and output. Example, you'll find CC configurations used in buffer stages and in devices that need to interface with other circuits without signal distortion. Slide 4. Common emitter, CE, configuration. Now let's look at the most popular configuration, common emitter, CE. Here, the emitter is the common terminal. Input is given between base and emitter, and output is taken between collector and emitter. This configuration is widely used in amplification circuits. CE configuration provides moderate to high current gain, moderate to high voltage gain. One key characteristic is that it causes phase inversion, meaning the output signal is 180 degrees out of phase with the input. The input impedance and output impedance are both moderate, giving it a balanced performance. This setup is suitable for general amplification purposes. Example, you'll find CE configurations in devices like microphones, radios, and speaker amplifiers. A new term here is phase inversion. It simply means that if the input goes high, the output goes low, and vice versa. Slide 5. Differences between CB, CC, and CE configurations. Now let's explore the differences clearly in point form based on key parameters. 1. Input impedance. CB has low input impedance, not ideal for signals from high impedance sources. CC has high input impedance, good for buffering. CE has medium input impedance, balanced use. 2. Output impedance. CB has high output impedance. CC has low output impedance. CE has medium output impedance. 3. Current gain. CB, low, less than 1. CC, high, approximately equals beta plus 1. CE, medium, depends on beta. 4. Voltage gain. CB and CE offer voltage gain. CC offers almost unity, 1 times. 5. Phase shift. CB and CC have no phase shift. CE causes 180 degree phase shift. 6. Application. CB, RF circuits. CC, buffering. CE, amplifiers. 7. Feedback sensitivity. CB is least sensitive to feedback. CE is moderately sensitive. CC also has low feedback issues. 8. Frequency response. CB is best for high frequencies. CE and CC have moderate response. 9. Usage level. CE is most used. CC is used for matching stages. CB is rare in practical systems. Each configuration plays a key role based on requirements like gain, impedance, and signal phase. Choosing the correct configuration is essential for effective circuit design.